Hi, this is Arash and welcome to the Epoxy channel. In this channel, we're going to talk about the epoxy resins from the theoretical aspects to the most practical ones. So if this is the first video you're watching or if you're interested in epoxy resins, please like and subscribe to our channel for more videos. Today, I'm going to present flame retardant fillers for epoxy resins. Fire is a chemical process that involves oxidation. Oxygen combines with hydrogen and carbon, which is then rearranged to form water and carbon dioxide. This energy causes heat generation in forms of an exothermic reaction where carbon burns to CO2. Epoxy resin is not flammable when it has been fully cured. Usually, epoxy resin can withstand up to 150 centigrade for a short period of time. Epoxy resin will not combust all by itself and would need a lot of exposure to heat and flame. However, heat-resistant epoxy resin can withstand extreme heat of up to 315 centigrades depending on the type of the product. Concerning epoxy system, exposure to uncontrolled heat, several factors have to be considered. These factors include epoxy system's ignitability, ease of extinguishing, flammability of the volatile product generated, rate of heat release, flame speed profile, smoke abstraction, and smoke toxicity. Flame-resistant product is a material that is inherently resistant to catching fire and shows self-extinguishing properties. Moreover, it does not melt or drip when exposed directly to extreme heat. On the other hand, flame retardant product is defined as a material that has been chemically treated for self-extinguish. Flame retardants are chemicals that are applied to materials to prevent the start or slow the spread of the fire. The most common classes of flame retardants are brominated, phosphorus, nitrogen, chlorinated, and inorganics. From another perspective, flame retardants that can be added to the epoxy system can be classified into different classes including halogen flame retardants, inorganic flame retardants, organophosphorus flame retardants, and fillers and nanofillers flame retardants. Halogen flame retardants include chlorinated and brominated flame retardants, and inorganic flame retardants include metallic hydroxide, boron, or nitrogen flame retardants. Flame retardancy can be formulated into epoxy resins based on two strategies: embedding flame retardancy in the curing agent or the base resin itself, or incorporation of flame retardant fillers and additives. In both scenarios, the aim is to inhibit, suppress, or delay the combustion. Halogenated epoxy resins show flame retardancy properties and contain various types, in particular brominated and fluorinated epoxy resins. Brominated bisphenol A is used when flame retardant properties are required, such as in some electrical applications. In the synthesis, the tetrabrominated bisphenol A or TBBPA can be added to the epoxy formulation. The formulation may then be reacted in the same way as the pure bisphenol A resin. Brominated epoxy resins are primarily used in applications where ignition resistance is required, such as in printed circuit boards and other applications that need to be flame retardant. Tetrabromobisphenol A is the largest flame retardant in terms of commercial use at present. It is used in an estimated 95% of all flame retardant printed wiring boards, and it is used in many flame retardant surface-mounted adhesives. It is manufactured by several producers, and it is priced as commodity product. The brominated resins are available primarily as semi-solid or solid in solvent solutions. They have properties similar to those of other diglycidyl ether bisphenol A epoxies, except that the high bromine content, 18 to 21% in the finished resins, provides outstanding flame ignition resistance. Tetrabromodiphenylol propane is an example of a commercially brominated epoxy resin. Standard epoxy resins are usually blended with brominated epoxy resins to provide the concentration of bromine required to provide ignition temperature resistance. Brominated resins have also been used as flame retardant additives in thermoplastic compounds. Brominated epoxy resins functions by liberating acid halide gases as the product thermally breaks down at the temperatures happen in a fire. These halide gases act as extinguishers to significantly increase the ignition temperature of the cured epoxy resins. The volume of gases liberated and the degree of flame resistance are dependent on the bromine content of the cured epoxy. Flame retardant curing agents for epoxy systems include organophosphorus polyols or halogenated anhydrides. Although the addition of halogenated flame retardants to epoxy resin matrices such as tetrabromobisphenol A or TBBPA is a fairly effective method to improve the flame retardancy of epoxy resins, upon combustion they produce a poisonous and corrosive smoke and can generate highly toxic halogenated compounds. That was, these resins are phasing out based on the environmental regulations. Halogenated and phosphorus-based flame retardants proved to be persistent, carcinogenic, bioaccumulative, and toxic for animal and human. Flame retardants have been shown to cause neurological damage and hormone disruption. They also can affect the endocrine, immune, and reproductive systems and cause cancer. Long-term chronic health problems as bodies contain higher and higher levels of these toxic chemicals. Flame retardants have the added problem of producing toxic gases when there is a fire, making fires more dangerous. Environmental activists, especially in Europe and Japan, tend to oppose the commercial use of halogen compounds such as bromine-containing flame retardant and tetrabromobisphenol A. The German Environmental Department, UBA, has issued a position paper in which it recommends phasing out tetrabromobisphenol A because it has been detected in the food chain. As a result, newer epoxy formulations are employing non-brominated flame retardant additives are commonly in use. Since the implementation of environmental derivative banning or limiting the use of halogenated compounds, the development of flame retardants based on epoxy resins has focused on more environmentally friendly alternatives. In recent years, a wide spectrum of new halogen-free flame retardants has been developed. A few of these systems can be seen here. Flame retardants can be incorporated as additives or as reagents, and in recent years, reagent-type formulations are gaining popularity due to their improved performance, although in general, they reduce the mechanical behavior, thermal resistance, and processability of epoxy resin composition containing them. In addition, flame retardant efficiency is low and combustion produces a large amount of smoke. Moreover, one of the greatest advantages of using a halogenated epoxy resins rather than an additive is the ability to maintain physical properties. Flame retardant additives work by acting chemically and or physically in the condensed phase or gas phase. Different types of flame retardant additives and their operating characteristics are char formers, heat absorbers, flame quenchers, and synergists. Char formers are usually phosphorus compounds which act by removing the carbon fuel source and providing an insulation layer against the fire's heat. Heat absorbers are often metal hydrates such as aluminum trihydrate or ATH or magnesium hydroxide and act by cooling the system by using the generated heat to evaporate water in their structure. Flame quenchers are usually bromine or chlorine-based halogen systems that interfere with the reactions in a flame. Finally, synergists, which are usually antimony compounds, enhance the performance of the flame quencher. Brominated epoxy resins function by liberating acid halide gases as the product thermally breaks down at the temperatures when the fire is happening. These halide gases act as extinguishers to significantly increase the ignition temperature of the cured epoxy resin. Currently, the metal hydroxide-based flame retardants are used most frequently, almost 56% of the total usage share, followed by the chlorinated and brominated ones, almost 20%, and organophosphorus is just 9%. In terms of applications, 36% of flame retardants are used in construction section, 32% used in transport section, 18% used in sport leisure, and 12% is used in electronic and electronics section. From another perspective, flame retardants for polymers can be classified as reactive, the flame retarding agents that reacts chemically with the polymer to become an integral part of the molecule, or additives, which are non-reactive agents that are simply blended or mixed into the compound. Flame retardants can also be classified by their major chemical groups. In a nutshell, we have different types: alumina trihydrates, magnesium-based, chlorines, bromines, phosphorus, antimony oxides, borates, silicones, and melamines. Alumina trihydrates are available in various particle size grades or in surface treated grades and can be used for polyesters, phenolics, polypropylene, and ethylene rubber compounds and epoxies as well. Magnesium type flame retardants include magnesium hydroxide and magnesium carbonate. These flame retardants products show synergistic effect with ATH for smoke reduction. Chlorines are a broad family including chlorinated paraffin, cycloaliphatic chlorines, chlorandic anhydride, methyl pentachloroacetate, and chlorinated phosphates. Chlorinated flame retardants are widely used for LDPE film and flexible PVC, urethane foam, and polypropylene and nylons. They are also used as reactive intermediate in making polyester and epoxy flame retardant resins. Bromines include aromatic bromines, aliphatic bromines, ionic bromines, benzene ethyl tribromo derivatives, and polypentabromobenzyl acrylates. Bromines are used to induce flame retardancy in polyolefins, ABS, polyesters, urethanes, foams, thermostats, and as a synergistic in engineering thermoplastic, glass reinforced nylon, and PBT. Phosphorus compounds include phosphate esters and other halogenated and non-halogenated compounds. They are often used in polyurethane foams, polyesters, and thermoplastics such as flexible PVC and modified PPO. They are also used for polyethylene, polypropylene, polystyrene, and ethylene propane copolymers. Antimony oxide is also has dusting and non-dusting grades which are available in various particle sizes which work synergistically with reactive or additive halogenated compounds. They can be used for ABS, polyethylene, polypropylene, polystyrene, thermoplastic polyester, and unsaturated polyesters. In borate family, we have zinc borate, barium, metaborates, ammonium, fluoroborates, and boric acid. Borates are used for flexible PVC, polyolefins, unsaturated polyesters, thermoplastic polyesters, epoxies, nylons, urethanes, and phenolics. Silicones such as polydimethylcyclosanes act as a producing a char surface and can be used for polyolefins, polyolefin blends, EVA, polycarbonate, and polyurethanes. Finally, melamines, including pure melamine, melamine derivative salts, for example, inorganic acids, and melamine homologues can be used for polyurethane, polyamides, polyolefin, and thermoplastic polyesters. Typical products applications and suppliers for these flame retardants have been presented here for your reference. It is common to formulate polymers with multiple flame retardants, typically a primary flame retardant plus a synergistic such as antimony oxide to enhance the overall flame resistance at the lowest cost. Selecting a flame retardant for an epoxy system could be very complex. It depends on the formulation being modified, the end use, how it will be processed, and the cost-performance ratio. Several factors should be considered when a flame retardant is chosen, such as water extraction, particle size, viscosity, toxicity, dusting, uniformity, as well as economies. The selected fire retardant materials must not interfere with the final product's performance. The major problem with incorporating flame retardants in adhesives is that very often a significant amount is required and they interfere with the other properties of the adhesives and contribute to the cost. This is why bromo-bisphenol epoxy resins are often employed in the flame retardant epoxy adhesives. The criteria in selecting and using the right flame retardant system for a specific adhesive formulation can be broad and somehow complex. Care must also be taken with regard to choosing the proper test method and determining the parameters of the test. Consultation with the flame retardant suppliers is generally necessary to optimize this process. Thanks for your attention. I hope you enjoyed the video. Please share your questions, thoughts, or comments, and I will come back to you soon. Thank you.